That's their answers. That's what I've been doing. How we've been starting, right? For 10, you should have gotten negative 0.239 meters per second. That was some kind of fraction in terms of pi. I forget what I didn't write down what the fraction was. Number 11 is 20 over 3 meters per second. Again, a decimal is fine. Is that like 6 2/3? Number 12 is 2.25 meters per second. And 13 is 3/5 meters per minute. And then 14 is 75 miles per hour. Okay. Questions from this set? Aaron.
Could you go over number 10?
Number 10. Sure. So it says water is draining from an inverted conical tank with a height of 10 meters, a radius of 4 meters. And then the water is draining at a rate of 3 cubic meters per minute. How fast is the height of the water changing when the water is 5 meters deep? So I'm going to start just by following kind of the format I'd given you guys. So there's like my conical tank, and over time, the tank isn't changing size, but like the height of the water is decreasing, right? So I know I'm going to be concerned with like the things that are changing are like the radius, the height, and the volume of the water, right? So far, so good. Okay. Let's identify, oh, we just did. Okay. So we have a variable for radius, a variable for height, a variable for volume. So each one of those, when we differentiate, is going to create a rate variable. We're told that dv dt is 3. How fast is the height of the water changing when the height is 5 meters deep? That's like what I'm looking for. This guy, though, we're not given. I can't proceed if I have 2 of these rate variables that are unknown. One unknown is fine if that's what I'm solving for. But a second rate variable unknown is big problems. What this tells me is that I need to eliminate R. So far, so good. So the piece that I haven't used yet that's been given to me is that we've given the dimensions of this tank as well, right? So that's what I'm going to use, or hopefully it stands to reason that that's what I'm going to need to use to eliminate that variable for R. So I have like radius for the tank, and then height for the tank. And ideally here, we would notice that like that forms 2 similar triangles. Very common trick when dealing with cones, water draining from cones. If you need to eliminate it, it's probably going to be the similar triangles trick that's going to be your tool to eliminate the variable. Or if you're given like a situation where you have two overlapping triangles, I think with like number 12 with the person walking away from the light, when you draw your picture, you're going to end up with, again, like two triangles nested inside of each other. Another similar triangle situation I think you'll need to use there. All right, so we can say that like radius of the tank over height of the tank is going to equal the radius of the water over the height of the water. So we know that this is 4 and this one is 10. So I know that like 10R is equal to 4H, or that R is equal to 4H over 10. So that's what I'm going to use for my eliminator. And again, the reason I knew that is because when I went down and wrote down my rate variables, like, okay, I'm going to have some rate variables, and I noticed suspiciously I have 2 that I don't know. One of them is the one I'm looking for. The other one I am not given any information about. I do not have enough information to calculate it. I cannot proceed with the problem with that R stuck in there because I can't let it generate a dr dt. So I have to do an elimination.
So how did you, so you know that H is equal to 10 and R is equal to 4. Where did you plug that in to get to 10 R is equal to 4H?
So RT is 4, HT is 10,
Okay.
and then I just cross multiply just to get the proportion, or to, to solve a proportion or whatever. And since I want to get R to be eliminated, I'm going to solve it in terms of R, so I can replace my R's with H's. Peyton.
Is the smaller triangle always going to be the one on top, or like the numerator, and the bigger part of it going to be in the denominator?
You can write that proportion any way you want. You could like have written it RT over R equals HT over T.
Okay.
Right?
Yeah.
So, or you could have written it as like R over RT equals H over HT. It's totally, as long as it like the corresponding parts line up either vertically or horizontally, it's a valid proportion.
Okay.
So that's totally on you on how you want to set up your proportion. As long as you set it up properly, they'll all simplify down to R equals the same thing.
Okay.
Is that okay?
Mm-hmm.
Okay. All right, so we have that. Hopefully you said that, okay, well, I know I'm going to need the volume formula for a cone. That's my base equation. And I'm going to substitute in my value for R, because I know it can't stay in there, and I'm going to call that 2/5 instead of 4/10. Everybody's okay with that? And do a little cleanup here. So 2 squared is 4. H squared times H is H cubed. 5 squared is 25 times 3 is 75. And now I'm ready to implicitly differentiate because I have no R, which is lovely because in addition to like, I'm not going to create a dr dt term, I also eliminate having to use a product property here because I just have H as the only variable on the right-hand side, which is so nice. I like the way it's working. Yes, sir.
So way back at the beginning, how did you find dH/dt equals 7? Did you just subtract the 10 meters from...
dH/dt is equal to 7?
Yeah.
That's a question.
That's a question mark.
Oh.
That's because that's what I'm looking for.
Yeah, I thought you were looking for dr/dt.
dr/dt is not given to me. I have no way to obtain it.
So like 2 unknowns?
Right, that's why I had to eliminate the R. Because the dH/dt is what I'm told to find. dr/dt is not given to me. I have no way of acquiring it. So I'm going to choose to eliminate the R. And then I won't form a dr/dt. And I don't have to worry about the fact that it's missing. And then from here, it's just plug and chug, right? We're told that H is, was it 5? Yep, is the instant we're worried about. And dH/dt is what we're solving for, and then just a little bit of algebra from here. Can I stop at this point, Erin?
Yeah.
So hopefully what you guys are going to notice, I gave you that procedure at the top of the page on like, do these steps. And it's really easy, like on the beginning problems, to be like, why do I need to worry about this? Why do I need to worry about this? And it's because when we get into the more complicated problems, if you don't identify the variables, and then like the ones that are actually variables, what their associated rate variable needs to be, and then look at the given values and see if you have a value for each rate variable, that is your cue for when you need to do an elimination of variable, right? That's why this is here. This is the first time where we've had to eliminate any unnecessary variable. This is the first problem so far from sets 1 and 2 where we've had to do that. Does that feel okay? And this is, again, I tried really hard when writing out this procedure to be like, okay, like what do I need to make sure in the hardest problem that I follow these steps to get to? So that's kind of what we're trying to do here. I'm like walking you guys forward. Lucas.
This is a simple question. Why, can you explain why dv/dt is not negative?
Oh my God, it should be. Thank you. Yeah, that's just a mistake on my part. Absolutely should be. Yes. Lucas, how did you know it was supposed to be negative?
Because it's draining.
Draining. So the volume is decreasing. It's losing. Yes, thank you. Very good. Whenever you see me making a mistake, make sure you stop. And even if it's not a mistake, if it was on purpose, if you're thinking that's a question, somebody else is for sure thinking that a question, and that's something worth addressing. Adrian.
Would you take like the fraction, or do you want like the decimal?
Either is fine. Like when you do the assessment for me, these are all going to be calculator problems. You can give me decimals, that is fine. You could leave it as a fraction, that is fine. I would accept either one. The AP would accept either one. Likely a question like this would be in the calculator section. This would be a likely free response calculator problem. Or part of a free response calculator problem. Hey.
Could you do 12, please?
12, that's the light one, right? Yeah. Okay. So let's just 10. I'm going to do 12 down here. It says a person 2 meters tall walks directly away from a street light that is 6 meters tall at a rate of 1.5 meters per second. How fast is the tip of the person's shadow moving when the person is 4 meters from the base of the light? Okay. So let's start by drawing our picture. And this one's maybe a little bit challenging to draw and label effectively. That's probably the hardest part of it. So this is like y of the light, this is y of the person. This is going to be like, call that x for the light. This would be like x for the person, and call that s for the shadow. Right? When the light's behind you, the shadow cast is in front of you. Does everybody feel okay with that? So I'm thinking about like this point, kind of like the origin, right? So the person is like xp over and the like yp up. You know, the end of that shadow is like, anyway. So let's think about this. So we have two constants here, right? The height of the person, the height of the lamp. And then as we're walking away, the XP is growing, right? So that's changing. The length of my shadow is going to do what as I'm walking away, right? It's going to be smaller. Everybody agree with that? And then the XL, don't think it matters, but I think that's variable. So, all right. So since these are all variables, they're all going to create a rate variable. Yes.
You kind of zoom in just a little bit. It's kind of hard to see. You don't have to.
I'm just trying to keep, I wanted the picture and all the stuff I'm writing on the screen at the same time.
Yeah, I'm sorry.
That's okay. This okay so far? Now, we're asked for, in the question, we're told that we're walking away at a rate of, let's go back to my things. At a rate of 1.5 meters per second. So that's this XP, right? So it's walking away from the lamp post. Is XP getting bigger or smaller? Bigger, so that should be a positive value. So 1.5. And we're asked for how fast is the tip of the shadow moving when the person is 4 meters. So that's the ds dt. And this guy we're not given. So we need to find an equation for XL in terms of the other variables. This should be very simple. Yeah, XP plus S, right? Everybody feel good on that one? A real brain buster there to come up with a second equation, but all right. So when I look at this guy, the equation that's going to relate the variables together I see similar triangles again. So everybody feel okay there? So I can say like YL over XL equals YP over S. Now YL and XL are constants, they're given to me, right? Or I'm sorry, YL and YP. No, I can't. There's no such 4 meter tall person. Mr. Kulik, what are you, nuts? It's like a 12-foot tall person. I'd be impressed. Let me just say that. You saw a 4 meter tall person walking down the street, you'd get into an accident because you'd what's going on? All right. And then XL, we know, is XP plus S. So far, so good. I'm going to cross multiply, so 6S is equal to 2XP plus 2S. I subtract 2S from both sides. And now we'll just differentiate. So ds dt is going to equal 2 times 1.5 over 4. So that is 0.75, right? So far, so good. Now, that's talking about, I guess we're not really looking for this, right? Because that's not the tip of the shadow. That's how this segment is changing, right? The tip of the shadow changing is also going to have to factor this in as well, though, right? Because this is like this guy's like our tip. Everybody's okay? My bad on that. Explained that poorly. Or minute, I guess, or something. Probably not meters per second. That's, what was meters per second? That's awfully fast. That's okay. It's a fast walker. 1.5 meters per second is like you're running. But hey, you know. Hey, does that feel okay?
Yeah.
And this last realization that the tip is really xp plus s, like that whole base segment is maybe not completely obvious until you think about when I explained it, hopefully like, well, it's this segment, the tip is moving with this piece, but it's also moving from this piece, so you have to like add those two rings together. When you think about it, it's like, okay, yeah, sure, that's how that's gotta work. When you think about it like in a physical sense when it's happening, right? But maybe not super obvious mathematically, which is part of the reason why this is like a set 3 level problem instead of like a set, 1 or 2, because I didn't really have to do much of a substitution here. The hard part was making that realization that when we talk about the tip, we're talking about this rate. Is that, you happy?
Yeah.
Yeah. Lucia?
For number 13,
Yes.
can you just draw out what it's supposed to look like?
Is that the rotating one?
Or that's the
It's a
triangular cross section?
Oh, the trough? Yeah. You guys spend a lot of time on the farm?
No.
No. Okay.
we didn't.
So like, we have one of these things kind of happening. Does that make sense or whatever?
Yeah, I just wasn't sure what it was supposed to look like.
Yeah, That's the the rectangular. It's like a thing you feed your animal in, right? If you watch Charlotte's Web, like the pig trough is kind of that shape. I'm trying to put a frame of reference on it. My daughter watched it, so I was like, well, maybe you guys watched it when you were little kids too. It's like 10 years old when I showed it to my daughter or whatever. She didn't really care. She liked the cartoon one better with the singing. And that's all you needed?
Yeah.
Okay. All right. We can always, again, in the future, come back and look at some more of these these third set ones. If you are like, okay, well, I'm gonna try some more and come back, like, that's okay. We can circle back and take some more questions next week when we meet again. Should we move on to set 4? Let's do that. Let me read through solutions here for set 4. So for 15, it's 1/2 meter per minute. 16 is 3.5 meters squared per second. -17 is -5/9 pi meters per minute. Oh, centimeters per minute, sorry. That was a C in front of it, must have been. And then our last one, 18, is 1/6 pi meters per minute.
You said 15 one more time, please.
Yeah, 15 is the first one, that is 1/2 meter per minute. Sure. Mhm. Where would you guys like to start on set 4?
Which one do you think is most challenging?
Well, I think visually, 18 is the most challenging because the setup is not like it's hard to picture what's going on. Which I think always makes these problems a little bit harder if you have trouble like picturing the scenario. I rely a lot on some imagination.
Me too.
To like figure out like what's a variable, what's changing, what's constant, and like to sort that out. So that would be my opinion. Is that what you want to do then? 18 says a cylindrical tank of radius 4 is being filled with water at 2 cubic meters per minute. A solid sphere floats in the tank such that the radius of the sphere is always equal to the water depth. How fast is the water depth changing when the water depth is 2 meters? Rough, right? Like not entirely clear what the picture is going to look like. So like, if we try to do this, so there's my cylinder, right? I'm just going to actually do that. I'm not going to give it a variable name. Okay. And now let's say that like this is the height of my water. Okay with that? So it means that like I have a sphere whose radius is the same as the height of the water. So like the bottom of the sphere is always going to be touching the bottom of the cylinder because the radius of the sphere is always the same as the height of the water. So the sphere is going to be growing as the tank fills. You guys see what's going on?
Like, is it like going up and then just stays at the halfway? Is That's like,
So let's do this again, right? Like, again, if you're having trouble picturing things, I like to draw a second picture that shows how things have changed with time. So that's my new water height. So this is now the radius of my sphere. So the sphere has grown now to occupy so that the radius of the sphere is still the same as the height of the water. Now, if you imagine, it's quite likely that at some point this sphere is going to like burst through the tank. So like if you're not careful and you pick the depth of the water is whatever, you can get like a nonsense answer out of this, most likely. Because I think physically what's going on, the sphere is gonna, the width of it is gonna be expanding past the width of the cylinder. And if it does that, then it's like, it breaks the whole problem. But that's kind of what's going on. Does everybody feel okay? So if I look at this, I have like 3 volumes going on in here, right? That are changing. And that's the tricky part. So what's one of the 3 volumes that's changing?
volume of the sphere.
The volume of the sphere is changing, right? Yes. Emma? Sure.
Volume of the tank.
So the volume of the cylinder is fixed, right? The volume of what? I'm sorry, you said. The water, yeah. Yeah, and how is the volume of the water?
Bigger, so we positive.
Isn't it equal to the radius? Or the change the radius?
So the height, so that's true. And we also have the volume of the cylinder of water, right? That's going to be changing because I have like a little cylinder of water here also, right? The tank itself is fixed, but that water is like a cylinder shape with a sphere cut out from it,
I'm a little bit,
or half a sphere cut out from it.
Why is volume of water and volume cylinder of water 2 different variables?
Because the volume of the water is going to equal the volume of the cylinder of the water minus 1/2 the volume of the sphere.
Oh.
Because that sphere is not, there's no water where the sphere is sitting, right? The water fills all the space around the sphere. And like, if the sphere wasn't there, it'd be a cylinder of water, right? But we have like a hemisphere cut out of that cylinder.
It's always half above and half.
Yeah, because the radius of the sphere is the same as the height of the water. So half the sphere is below the water and half the sphere is above.
Gotcha.
Is that like, is it the displacement of the water, or is it the water that's like missing, or the water around? Like,
So-
which is it representing?
So volume of the water is the amount of water in the tank.
Okay,
Now the shape of that water is going to be like a cylinder with a hemisphere cut out from it,
Okay.
right?
yeah,
The volume of the cylinder of water is imagining if the sphere wasn't there.
so the water would be lower, or,
We're just pretending like it's the same height of water,
okay,
but the sphere is not there, because that's how we're going to calculate the volume of the water.
okay,
Because coming up with a volume formula for a cylinder with a hemisphere cut out from it,
mhm,
it's like, I don't know what to do with that. But if it was a plain cylinder and then subtract the hemisphere out of that I can do.
okay, yeah.
Does that make sense?
Yeah, I get it now.
Okay.
what would happen if the water continued to rise? Would the radius get smaller then?
Well, eventually the sphere is probably going to break the tank.
Okay,
Because usually your cylinder is not wider than it is tall.
just confused with what.
I mean, it would be like
No, I mean.
the Incredible Hulk bursting out of its clothes. I don't know, I'm just trying to come up with an analogy.
It's just a confusing concept.
Yeah, that, and again, that's why Peyton asked which one she thought was the hardest, and I thought it's this one, mostly because the picture is hard to imagine, right? Once you've got it, it's like, okay, this is the hardest piece, coming up with this realization that that's what we're looking for.
It's just the sphere is getting bigger when the length between the ground and the surface of the water gets bigger,
The what is, I'm sorry,
right? The sphere is getting bigger as the length between the ground and the water is getting bigger.
correct, as the height of the water increases, the sphere's radius increases, which means the whole thing gets bigger. Yes.
Do you come up with these on your own?
I had ChatGPT help me with the writing of these problems.
Yeah, that explains.
So like I talked through like, hey, I want something that includes, you know, like similar triangles and elimination variables, and I want some water draining problems, and like gave some descriptions of problem types,
ChatGPT is awesome.
and then it'll like help me fill in and gave me prompts that were had real answers to it. And like this one initially, the answer is like, oh, it just breaks the thing. I'm like, no, I don't want it to break the thing. Can we give it like an answer that has like a real, like still has a numeric value and doesn't like break the problem? And they're like, okay, yeah, sure, we can do that. Like we go back and forth about updating these things because it's a pretty good problem generator.
I'm sure. I would have been impressed if you came up with this by yourself.
Yeah.
Yeah.
It's pretty interesting.
This is not a uncommon example
Really?
of a hard related rates problem where you have like one thing occupying space that's growing as more, you know, like as water's coming in. This is not a absurd problem.
It's like
Would it be like, it's going to be like a sponge?
yeah.
Yeah, or even like,
balloon blowing air.
yes, like think about like you have a balloon underwater that's like volume's coming into the balloon, and that's displacing water, and you could also have water coming in or coming out at the same time, and like, you know.
This is how Harvard is.
This is how what?
Harvard is.
Okay. I don't know much about mechanical engineering, but it wouldn't surprise me. Okay. Should we continue on here?
Yeah.
Okay. I also know that like, I observed that like the radius of the sphere, we're told is equal to the height of the cylinder of water. Everybody's okay there? And that's all variable. So I'm gonna have a dvs dt. I'm gonna get a dvcw dt. I'm gonna get a drs dt, but that's gonna just be equal to dhcw dt. I'll note that the radius of the cylinder of water is constant, because that's just the radius of the tank, right? Everybody's okay with that? Like, that circle of water there at the top has always got the same radius because the tank is a cylinder as opposed to a cone. Well, that's nice, right? Yeah, that makes a big ding dong difference.
That's the nice part. Everyone else is.
And we are looking for
What's the constant?
the radius of the cylinder of water.
Oh, radius of the sphere equals.
Yeah.
Yeah, that's what that says.
Yeah.
I can tell constant.
Right? Because the cylinder of water is gonna be the same radius as the tank, the cylinder of the tank,
Okay.
right? Like if you have a can of soda and you look at it at the start, you drink some out of it, you set it down, the radius of the cylinder of Coke is the same at the start as the end.
Unless it's
Well, yeah, but isn't the radius getting bigger and the radius is like the whole sphere?
We're talking about the cylinder of water,
Okay.
okay? Not the sphere. So if I take this then, the volume formula for a cylinder is pi r squared times height. The volume for a sphere is 4/3 pi r cubed. And I know that the radius for that cylinder of water is just 4. And I know that the height of the cylinder of water and the radius of the sphere are the same, so I'm just going to call this, forget which one, what was it asking for? How fast is the depth of the water changing? So let's call this all heights of water. Oops.
Wait, it's just so that drdt and dhdt are the same.
Right. That those two rates will be the same because the variables are the same, right? So we're going to have 16 pi, and I'm just going to call this h now for Ren drop the CWs. And then I'm going to have, minus 2/3 pi, and I'm just going to call this h again and drop the CWs. This is what I was looking for. When the height is something 2 or something. Is that what it says? I dropped my sheet. Oh, it's so far down. The depth is 1, right? Okay. So now we can just differentiate. We're told that water's coming in at 2, being poured in, and the height at the time or the instant we're interested is 1. And now it's just some algebra to the finish line, I think. Does that feel okay, guys? And that's quite hard. It's a quite hard problem. Because physically, it's really difficult to picture what's going on.
Yeah.
Would
Right.
you give us something like that on the?
On your thing?
Yeah.
Probably not. Your freshman year calculus teacher at college probably will.
That's great.
So,
Do we have to take,
depends on what your degree is.
I love that.
Depends on what your degree is.
so I'm not gonna be an engineer
Okay.
or a math teacher.
Okay.
So I think I'm chill.
I mean, depends what you're studying. There's lots of other subjects that require calculus as like a prerequisite.
What was the final answer for AT?
I forget what I said. I said 1/6 pi, but now when I'm looking at my work, I think I forgot the 1/2 in front of the sphere, so I might be off on that.
I got 1/2.
You got 1/2 pi? Well, it should be positive. Definitely needs to be a positive value.
Because it was minus 2.
Yeah. Let's, so let's just do this real quick, algebra Y. So those guys cancel out, right? So I'm going to have 16 pi dH dt minus 2 pi dH dt. So I have like 14 pi dH dt. And I divide both sides by 14 pi, so I'd have 2 over 14 pi dH dt, or it should be 1/7 pi. Does that feel okay? So 1/7 pi would be our answer instead of 1/6 pi. So if you wrote down answers, update that for yourselves. Adrian.
First 16.
Yeah.
Would you have to eliminate like dw, dt?
So for 16, it says a rectangle with a fixed diagonal of 10 meters. The length of the rectangle is increasing by 1 meters per second. How fast is the area of the rectangle changing when the length is 6 meters? Yes, you'll absolutely need to eliminate the W because you're not given how to find dw dt or given dw dt. So that's 100% what you need to do. Very good. Yes, absolutely.
Yeah, I just don't know how to do it.
Pythagorean theorem. Because you have the diagonal, and that's a fixed value, right?
I was using area.
Ah,
Like,
yeah. It's not going to work because you need the area to differentiate. So you need a second equation, Pythagorean theorem, because it's a rectangle, and you have the diagonal.
so both?
Yes, because you're going to use, you'll have like this, and then you have that, and you're going to eliminate the W from this equation using this one. Right?
Oh, so it'd just be w is d squared minus l squared per square.
Yeah. And then you can drop that into here.
Okay.
And since D is a constant,
Wouldn't that just be d minus l?
square roots don't distribute across addition and subtraction. Yeah, it's a chain rule derivative.
Okay.
So when you take the derivative, what would it be?
So you have that, right? Now, the way it's currently written, it's a product rule and a chain rule. I don't love that. And I think the D, it says the diagonal is 10, right? So let's just write that as 10. So what I'm going to do is I'm going to think about L as that, the square root of L squared, and that allows me to push it inside and get rid of a product rule, which to me sounds like a good deal. If you don't do that, that's fine, just do a product rule. So dA dt then is going to be 1/2 100 L squared minus L to the 4th to the negative 1/2 times the derivative of L squared minus L to the 4th and then we have dL dt. Sorry.
It's more complicated.
Yeah.
That isn't something nothing.
It's a big.
It does. I mean, it seems like such an easy phrasing, right? The problem is that you're not given the dw dt. That's what makes that much more difficult.
Yeah.
Hey,
So when you're solving or like trying to eliminate a variable, it's either gonna be similar triangles or you have to come up with another equation.
yeah, you'll have to come up with a second equation no matter what to do the elimination, unless they've like implied it inside the problem,
Okay.
right? Like in that floating sphere problem, you told us that the height of the water was the same as the radius of the sphere, so that's like your equation that you needed to eliminate
Okay.
a variable with. Sometimes they just tell you, and sometimes it's like you have to get it from the situation. So like here, you had to realize that like you had a Pythagorean theorem thing going on. Right. For the most part, the hardest relationship to see are the similar triangle ones, because you have to see it in the problem. It's usually easy to be like, well, it's a right triangle, so I know I can do the Pythagorean theorem. That one's typically students don't miss when they're looking for the second equation. That one's typically pretty easy to find. What do we have left in class here?
10 minutes.
Well, I want to start because I have enough time to tie the bow on what we've been doing, and I really want to tie this bow. So when we go in and go in more detail, you've had a weekend to kind of let that settle and sink in a little bit. So remember, we're working on these two different ideas. We had this antiderivative process, we had this area under the curve, or integral process, right? And today we're going to marry those two things together. I'm not at the top. All right, go. All right. So what I'm going to do is I'm going to define a new function. I'm going to call this function g of x equals the integral from a to x of f of t dt. This is like the area under the curve so far function. Everybody okay with that idea? So like if it's, if a is 1 and I go to 2, it's like, well, it's the area under the curve from 1 to 2. If a is 1 and then x is 3, then it's area up to 3, where it's now like an area function, like the area so far function. Is that okay? Okay. So if I wanted to do this, if I have my function g of x equals the integral from 0 to x of f of t dt, and I want to calculate these values for g of x, and I'm given this curve, well, I have like, if g is 0, then I plug 0 in for x, and if the upper and lower bound are the same, we know that integral is 0, right? If g is 1, then from 0 to 1 is that triangle. So I calculate the area of that triangle. If g is 2, it's going to be the triangle plus this rectangle, right? And you guys get the idea here, right? Okay. So this is like an area so far function. And if I went ahead and graphed this that looked like a function, this would be like what the curve would have looked like. Okay? Fine. Here's what I really want to get to, is the relationship between the derivative of g and that function inside of it, f, that we're finding the area under the curve for. Okay? We'll go through this maybe in a little bit more detail when I have a minute, but here's what I want you to see. The derivative of g was just f of x. What have we just done?
So they cut out the word.
Oh, even better than this. To undo an integral, To cancel out the integral, you take the derivative. Oh, does that mean then to cancel out a derivative, I can just take the integral? Yes, that the two operations are like inverses of each other. To undo one, you just do the other. So what we have here then is the fundamental theorem of calculus part 1. It says if f is continuous on the closed interval from a to b, then the function g defined by this area so far function, blah, 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 is continuous and differentiable, and the derivative of g is f of x. So if I take the derivative of like both sides, it just cancels out the integral. That's what it's saying. Part 1 is just saying that derivatives and integrals cancel each other out, like multiplication, division do, or squares and square roots do. You can use them as inverse operations of each other. That's essentially what it's saying. Really cool. Okay. Some examples. Part 2. What this means then, if I have the integral from a to b of f of x dx, and I want to compute the area under that curve, I can do the antiderivative of f, evaluated at b, minus the antiderivative of a, or of f, evaluated at a. No longer do I need to do the limit of Riemann sums. I've now connected the antiderivative to this area under the curve calculation. How much easier does that make life than having to grind through those terrible limits and summations and all that nonsense? It just becomes the antiderivative, which was fairly easy to do, at least in the circumstances we started with, right? Yeah. That's the payoff. We'll go through this again on Tuesday or on Wednesday in much more detail. We'll start at the beginning again. But this is what I wanted to get to, at least give you the payoff before you get into the weekend, to show you the light at the end of this tunnel and how we're going to, marry these ideas together and get away from having to do the limit of those Riemann sums because nobody likes that. How wonderful is the payoff here? Like, oh,
Yeah.
oh, yeah.
What was the answer for
16 from the on the related rates. 16's that 3.5.
So, Alice, are you going to do that?
So tentatively, we'll see when you guys check in again on Wednesday, but tentatively, let's plan for the related rates on Friday of next week. Okay, tentatively. Again, we'll check in on Wednesday and take a temperature, but Friday next week, related rates, 45-minute cap, because I told you the format already, right?
Yeah. It'd be like
5 multiple choice, there's 3 regular free response ones, we choose 2 of the 3 to do.
30 points, you said?
30 points total, 2 points per multiple choice, 10 points per free response. There'll be points for like drawing the picture and identifying variables and stuff like that. So if we can do the process and make some goof, we can still gather most of the points there. Trying to make life, again, more manageable for you guys. Does everybody feel okay? Adrian?
So would like the 5 multiple choice be more like set 1 and 2?
Yes, the 5 multiple choice would be like set 1 and 2, and the free response like 3 and 4. Exactly right. And you'll likely on the free response ones, you'll see repeated scenarios. Like the setup scenario, like water draining from a tank, or like person walking away from a light, or you'll see me reusing the scenarios that we've already presented to you.
Because I think the big thing for me, like, I'm struggling with is like making equations.
Yeah. If you practice the ones that I've given you, the setup is going to be very simple. So that's, your best preparation is to go through that again, because I tried to gather like all of the most common related concepts.
Also, can I see it set to, I can come back and see it.
Do you need an extra copy or you want hands?
No, it's like, I messed up the first one and I went.
1 year is
Okay.
20 years. Or not so. Second.
It's just that you have to write essays
Yeah.
and
One test.
It's just
I
Yeah.
thought like,
You
I
have to
got
hide
knocked
which
out.
was not.
Which was fine. And even that, it's mostly correct. Even that,
The concept.
environmental studies, so
A lot of your own, like,
like somewhere. Okay, stop. Just go.
Oh.
You just hand it up? Okay. Oh, no problem. I just checking.
Matt, you did, tackle if it was.
No, like